Hello, students. We're back to finish up our topic on energy. But before we do, please all together tell me, what is energy? Hopefully, you shared with me that energy is the ability to do work or cause change. And hopefully you will remember that for as long as you live. But today we're going to take energy one step further, and we're going to talk about two states of energy. One state of energy is over here, Kinetic Energy. And no, I'm just kidding. I'm just kidding. No, Connecticut is not one of the states of energy, but kinetic is. This is a great video. If you haven't had a chance to watch it, I would ask you to watch it later on today, perhaps. But let's get into a more interesting video to introduce this segment on two states of energy. So I love cartoons. Do any of you love cartoons? I'm going to show you a couple of cartoons today. So let's watch this first cartoon to introduce the concept of two states of energy that we're going to explore at greater length this period. So let's watch, listen, and learn.
Suppose you wanted to move a large log. That would take energy. Where could you get the energy to do it? One place, of course, is from your own muscles. You could supply the energy to push the log. Or someone else could supply the energy. Then the energy would come from someone else's muscles. Or you could use a machine, like this bulldozer. Then you'd be getting the energy from gasoline. Or you could even use an electric motor. Then the energy to move the log would come from electricity. But let's say you didn't have a friend to help you. And let's say, at least for now, that there weren't any machines around that use gasoline or electricity. Then where could you get the energy to move the log? You could still use your muscles, of course, or the muscles of other animals. But are there still other things around you that might have energy that you could use? Well, here's a small rock. Suppose you wanted to crack it in two. That would take energy. Where could that energy come from? Suppose this happens. The energy to break the rock in two came from the large rock that fell. But wait a minute. There is energy in a rock? How can that be? It doesn't look like there's energy in the rock now. But there was when it fell. What's going on here? The answer is that when the rock was falling, it had a special kind of energy called kinetic energy. All that really means is that it was moving. And because it had kinetic energy, it was able to apply a force to something else by falling on it.
So let's pick up on that idea of a falling rock as a state of energy. There are actually two states of energy, and the first one is that word that he mentioned, kinetic. Kinetic energy comes from the Greek word kinetikos, which means motion. Have any of you ever played with kinetic sand, by the way? Kinetic sand is kind of cool, and it moves in a very interesting way. A kinetoscope. A kinetoscope is a device that allows you to see something in motion. Have any of you ever taken like a pad of paper and drawn little stick figures on it in slightly different positions, and then go like this with the pad of paper, and you can see the objects moving? That's a type of kinetoscope, or a device that makes things look like they're moving. Anyway, back to science here. Kinetic. Greek kinetikos, which means motion, because kinetic energy is energy in motion or energy of motion. Kind of like we were talking about yesterday, one of the forms of energy is mechanical energy. Energy is matter in motion. Well, kinetic energy is a state of energy. It can include a number of different kinds of forms of energy, but kinetic energy, energy of motion. So keep in mind kinetikos, motion, kinetic energy, energy of motion. Now, it depends upon a couple things here. Kinetic energy depends upon mass and velocity. If we were to think about that example of that boulder falling off the hill again, what kind of connection could you come up with in terms of the impact of the fall based on how high that boulder was or how big that boulder was? I want you to think about. Let's pause and discuss for a moment. What would you expect if the boulder was bigger or smaller, and what would you expect if it was higher or lower? Pause. All right, maybe you had the opportunity to discuss how you thought a bigger boulder could do more damage to that smaller rock down at the bottom of the hill because it's going to have more mass, it's going to have more kinetic energy as it's falling. And likewise, if it's up higher, it's going to be falling faster, it will have a greater velocity. So also, it's going to do more damage. So kinetic energy depends upon the mass and velocity of an object. And as you know, in science, especially in physics, we love to take these relationships between things and turn them into formulas or equations. And here is the equation for kinetic energy. We can write it in a couple different ways. Kinetic energy is equal to mv squared, where m is equal to mass, v is equal to velocity, divided by 2. Or we could say kinetic energy is equal to 1/2 mv squared. It's exactly the same thing mathematically either way, and that has to do with the order of operations in mathematics. Can any of you think of a memory aid from mathematics, from math class, regarding the order of operations? Maybe you remember PEMDAS, or please excuse my dear Aunt Sally. She had too much Taco Bell last night. No, just kidding. That PEMDAS, those letters, the order of operations, parentheses, exponents come before multiplication and division, which is why this is exactly the same as this. But no matter which way you remember or memorize this equation, it's the same. Kinetic energy is equal to 1/2 mv squared, or mv squared, all divided by 2. And again, m is mass, v is velocity, and there is a relationship. In fact, tomorrow's lab activity involves discovering the relationship between kinetic energy, mass, and velocity. So, as we're thinking of kinetic energy right now as one of the two states, we're going to introduce the second state of energy with another cartoon. I hope you enjoy this one as much as I do, because these are my favorite cartoons of all time. Check it out. think you get the idea. Poor Coyote and Roadrunner, they're constantly experiencing two states of energy: kinetic energy, and you probably guessed the other one by now, potential energy. And there are different kinds of potential energy, as you saw in that little cartoon clip. But generally speaking, potential energy is energy of position. Think of the first two letters of the word, P-O, potential. Think of P-O, position. Think of popo, potential, position. Potential energy is the energy of position. And this individual here, what is he doing? Getting ready to jump off a cliff. I don't know why anyone would want to do that in their right mind, but right now he's got a lot of potential energy. And in a short period of time, that potential energy will be converted into kinetic energy until he hits the bottom of the cliff, in which case he will have no energy left to do anything else. But let's talk more about potential energy here, energy of position. Another way of thinking of potential energy is that it is stored energy. And there are different ways that potential energy can be stored. One way is, as we see here, as energy of position by a suspended object. An object raised up like a ball. This ball, for instance, right now has a lot of potential energy until I let go. And then it has energy of motion or kinetic energy. So potential energy can exist with suspended objects. It can also exist in the form of fuel, like in a car, or as we saw in that cartoon clip, kinetic energy, or rather potential energy, can be stored in springs as well. Let's see if I can demonstrate this little robot on a track here. I have wound up a spring, and check it out. He is walking because of the potential energy from the spring has been converted into kinetic energy, or energy of motion. Another way to think of potential energy is taking place inside your body every time you eat something. When you eat, and hopefully you all eat a healthy breakfast, when you eat food, food has the potential to provide you energy throughout the entire day. Food is an example of stored chemical energy. Thereby, it has potential to fuel you throughout the day. But you live by moving around kinetic energy, and that kinetic energy is a transference from the potential energy of all of the calories that you have consumed previous to moving. So, potential energy could be in food, fuel, suspended objects, etc. Now, there's a phrase here for you to remember when it comes to potential energy, and it is: the bigger they are, the harder they fall. We spoke of this briefly, if you recall, regarding the boulder on the cliff. The bigger they are, the harder they fall. I have two balls. One is bigger than the other. Okay. If I drop both of them from the same height, which one do you think has more energy? Woo! Okay. Which one do you think has more energy? The big one or the little one? Well, the big one does. Why? Because it is more massive. It is a bigger mass. And so, Again, we're talking about relationships between things in science with physics. There must be an equation or formula here for potential energy, and yes, there is. Potential energy, PE, is equal to the mass of an object times the gravitational pull on that object times the height of that object lifted above the ground. So there are three variables that are connected here to potential energy: the mass, the height, and the gravitational pull on an object. And we can calculate potential energy by multiplying these three things together: mass times gravity times height. Now, the relationship between potential energy and kinetic energy is something I am sure many of you have experienced in your lifetime. How many of you have ever been to an amusement park? Maybe some of you have gone on rides like this one here. And if you haven't, maybe you've been outside to a park at some point in your lives and have been on a swing, because the same thing happens on a small swing or a big swing like this one. I can't go on rides like this. They make me a little bit queasy, the back and forth motion. But we've got a rocking ship here, basically. And at this point in time, when it is suspended as high as it will get, there is a point in time when it's not moving at all. And at that point, it has no kinetic energy. It's got all potential energy. But once gravity starts pulling it down, however, and it swings up the other direction, there becomes a point at the very bottom when it is moving as fast as it can. It's got all kinetic energy, but it's at its lowest point, so it has no more potential energy. And then it swings up the other direction, and it goes back and forth, back and forth. And there's this transfer that exists between potential energy and kinetic energy. And I want to illustrate it to you with this graph. As that swing goes back and forth, there is a point where it has all potential energy and no kinetic energy. But as it swings, all that kinetic energy is in motion, and there's no potential energy until it swings back up the other direction. It goes back and forth, back and forth. Here's another way of looking at the relationship between potential and kinetic energy in terms of a ball rolling down a hill. At the top of the hill, before the ball is moving, it's got all potential energy and no kinetic energy. As it starts to roll down the hill, notice what happens between the relationship of potential versus kinetic energy. By the time it reaches the bottom of the hill, it's totally in motion. It's got all kinetic energy and no potential energy. So yesterday we talked about forms of energy. Today we talked about the two states of energy. But there's another connection with energy that I want to emphasize you today before we end, and that is involved with the conversion of energy. Energy can be transferred from one object to another and from one form to another. But another part of this is that energy cannot be created or destroyed. Neither can matter. Neither matter nor energy can be created or destroyed. It can only be changed in form, from one form to another form. So I'm going to show you an example here, a famous example or popular example of how energy can be seen to transfer from one object to another. Perhaps you recognize this. This is called Newton's cradle. But I've got a great little video we're going to finish with here regarding some experiments that can be done with Newton's cradle. So, and before we'll show you the video first, okay? And then I'll finish up with a little funny cartoon. So, check out this little video clip of Newton's cradle. Notice how one ball lifted on this side was the potential energy was transformed into kinetic energy, and that energy was transferred through the other balls and made one ball on the other side fly off. Now watch what happens when he takes two. Conservation of energy. Two on one side, two on the other side. What would be your prediction now with the lifting of three balls? Let's find out. Pretty cool, huh? Conservation of energy. Oh my. Hold on a second. What do you think is going to happen now? It's lifting four on one side, but there's only one left. What do you think is going to happen? Let's find out. Check it out. Conservation of energy. Energy is conserved. Now let's have some fun and watch some of these other demonstrations here. Let's see what happens. Yeah, horsey. Sounds like a galloping horse. Whoop. Using the camera. Now watch this one. Oh my. Whoop. Pretty cool, wouldn't you say? I'd say that was pretty cool. If you want to see the rest of the cool experiments, go back on the notes and check that one out. That's pretty wild, I think. But we're going to finish up with this little cartoon here. And this is why science teachers should not be given playground duty. I'm not going to show you the video for this. No one was hurt in the making of this video, but if you want to see it, you'll have to watch it on your own time. Because right now, I would like you to utilize the remainder of your time to work on the practice problems at the end of your notes section, because we're going to put that material into practice with tomorrow's lab activity. So I'm going to end the video now, and then you can have the rest of the time to talk together as a class on how this should be done and use the example problem in your notes to help you out. So for now, I'm going to say bye-bye.